Hello, and welcome to Course 102's Day 3 Rewind. Today, we are going to be recapping the sections of a power supply, the half-wave rectifier, the full-wave rectifier, the bridge rectifier, along with the Zener diode. So the first thing we're going to touch on is the breakdown of a power supply. The purpose of a power supply is to turn AC into DC. A power supply consists of 5 sections, the first one being the input section. In the input section, it is going to have a transformer in it that's going to either step up or step down the incoming AC voltage. Now that stepped up or stepped down AC output is going to get fed into the next section called the rectifier. And the purpose of that rectifier is going to convert that AC into a pulsating DC signal, kind of like this. That pulsating DC signal is going to get fed into the next section, the filter section, which is going to take that very pulsating DC input and turn it into a smooth, unregulated DC output, kind of like that. That's going to feed into our fourth section, which is the regulator section. Now this section is key because its purpose is to maintain a constant DC output signal, or DC output voltage. The last section is going to be the protection section, and it's going to utilize a fuse or circuit breaker to protect the circuit from overload. With that being said, let's move on to our next circuit, the half-wave rectifier. The purpose of a half-wave rectifier is to convert AC into pulsating DC, and T1 is going to step up or step down the incoming AC signal. When the top of T1 alternates positive, we're going to forward bias D1. When this happens, we're going to provide a path for current flow. Current is actually going to get pulled up from ground through our load resistor RL, developing a positive going voltage drop on our output. The complete path for current flow is ground through RL, through our forward bias D1, all the way back to the top of T1 because current flows from negative to positive. But when the signal alternates negative, the top of T1 is negative, we're going to actually reverse bias D1. And a reversed bias diode acts like an open. So at this point, there is no path for current flow. So the entire portion of the negative alternation coming in on the top of T1, our output will be 0. And this process will repeat every time the signal alternates positive. To calculate the average DC output, just ensure that you refer to Table 5 on your formula sheets as we discussed in lecture. Now let's move on to our next circuit, the full-wave rectifier. The purpose of a full-wave rectifier is to convert AC into pulsating DC. T1 is going to step down the incoming AC 2 to 1. Meaning that whatever is on the primary is going to be 1/2 of that on the secondary. If the top of T1 is positive, the bottom of T1 is negative, and vice versa. When the top of T1 is positive, D1 will be forward biased and provide a path for current flow. Current will flow up through our load resistor, developing a positive going voltage drop. Current will continue to flow through D1 back to the top of T1 because current flows from negative to positive. When the bottom of T1 is positive, the top is negative, we're going to forward bias D2, meaning that our other diode is reverse biased. With D2 forward biased, we provide another path for current flow. Current's going to flow upwards through RL, same as before, developing that positive going voltage drop on our output. Current will continue to flow. Instead of going through D1 this time, we're actually going to go through D2 to the bottom of T1. And that process is going to repeat as the positive and negative alternations of the waveform come in. Lastly, again, to calculate the average DC output, please reference Table 5 of your formula sheets. Now, let's move on to our final rectifier circuit, the bridge rectifier. The purpose of a bridge rectifier is to convert AC into pulsating DC. Again, T1 is going to step up or step down our incoming AC voltage. When the top of T1 alternates positive, we know that the bottom of T1 is negative. With the top of T1 positive, we know that D2 is going to be forward biased. Additionally, with the bottom of T1 negative, we know that D4 is going to be forward biased. So we can say that the other two diodes are reverse biased, so no current will flow through them. Current is going to originate as it flows negative to positive from the bottom alternation, or the bottom of T1. So we're going to flow from the bottom of T1 through our forward biased diode D4, and in circuits, ground is electrically connected. So we flow through ground and upwards through our load resistor. When this happens, we develop our positive going voltage drop on our output. And current continues to flow negative to positive through our forward biased D2 all the way back to the top of T1. And then the top of T1 is going to go negative. So the bottom of T1 is going to alternate positive. When this happens, we can say that D1 is forward biased and D3 is forward biased, meaning the other two diodes, again, are reverse biased. Since current flows from negative to positive, we'll start at the top of T1. Current will flow through our forward biased D1. Again, we'll flow through ground because it's electrically connected. And then we will flow upwards through RL, again, developing that positive going voltage drop, creating that pulsating DC. Current continues to flow through our forward bias D3 all the way to the positive bottom of T1. And then this cycle will continue to repeat over and over, producing that good pulsating DC output. The last thing is calculating the average DC output, which you can do by referencing your formula sheet, Table 5. Now, let's move on to the last thing we were going to recap today, the Zener diode, the purpose of which is that it's used as a voltage regulator. Now, when dealing with a Zener diode, the first thing we need to ask ourselves is it forward or reverse biased? Once we know, let's say it's forward biased, meaning we have a positive potential on the P material and a more negative potential on the N material. It will conduct, and if you measured across it with a voltmeter, it would have a voltage drop of 0.7 volts. But when it's reverse biased, on the other hand, meaning we have a negative potential on the P material and a positive potential on the N material, we have to ask ourselves two more questions. A Zener diode will have a VZ, or breakover voltage rating, attached to it. For instance, this one I'm going to give a VZ of 5. Now we have to ask ourselves, is the voltage applied above or below the VZ? If it's above, let's say we put 12 volts on the N material and 0 volts on the P material, that value exceeds the VZ of 5. In this case, it will conduct, and it will, if you measured across it, it would have a voltage drop equal to the VZ. But if we apply a voltage, let's say, in this case, 4 volts with 0 volts on the P material. That value is less than our VZ, and in this case, it will act like an open switch and will not conduct. This concludes our Day 3 rewind for Course 102. Thank you for listening.